Hey, this is Mr. James. In this video, we'll talk about applications of factoring. But first, a quick discussion on why do we factor and why is this actually useful? Well, the first way it's useful is it helps us find roots or zeros of polynomial functions and use those to get the x-intercepts to be able to graph them. If you think back to quadratic equations and quadratic functions, you'll remember that we often found the zeros or the roots of a quadratic, which are the same as the x-intercepts, in order to better graph those quadratics. We'll do the same thing with polynomials. However, this time they may have more than two zeros or x-intercepts. They could have three or many, and so we'll need to factor to find those. Factoring is also useful for solving polynomial equations when they're set equal to 0. Think back again to quadratics. Suppose we have a quadratic equation like this. -6 equals x squared plus 5x. We first had to get all the terms to one side of the equation so that it was set equal to 0. For example, we have that right here. And then we would factor, right? Factor something like this. And then we would use the zero product property, the fact that if this whole expression is equal to 0, then each of those factors, or at least one of those factors, must be equal to 0. We use that to solve our equation. So x must equal either -2 or x must equal -3. We'll do the same exact thing with polynomials, however they may have a few more factors than just 2. Lastly, factoring is also important for dividing polynomial expressions. Think about maybe dividing or simplifying what we already know how to do, so maybe integers. Take, for example, the fraction 6/4, 6 over 4. If I wanted to simplify that, or maybe reduce that, I would know that's the same as 3 over 2. But the reason I know that is because 6 can be rewritten as 2 times 3, and 4 can be rewritten as 2 times 2, and the common factor of 2 over 2, 2 divided by 2 is 1, so that's 1 times 3 over 2, and 1 times anything is just that thing, so that's the same as 3 divided by 2. And so this common factor on the top and bottom was critical to simplifying that fraction. The same will happen with polynomials. Suppose I have some long polynomial expression in the numerator and in the denominator of maybe a fraction, right? They're being divided. If I can somehow factor those polynomials and then find out that 2 or more of those polynomial factors are the same, then I know that they will divide to equal 1, and I'm left with a much smaller polynomial to work with. So what are its limitations if factoring is so useful? Well, it turns out that not all polynomials can be factored. In fact, most cannot. Think about when we talked about quadratics earlier this year. We saw things like x squared plus 2. That cannot be factored any further. You might think it's a difference of 2 squares, but there's a plus sign there. It's not a difference, and 2 is not even a square number. So there exist many things like this factor right here in higher order polynomials. Furthermore, if you end up with an unfactorable quadratic factor, such as x squared plus 4 or x squared plus 5x plus 9, you might still have to use the quadratic equation, and you might still have irrational or imaginary numbers as solutions. Such factors are sometimes called prime or irreducible because they cannot be factored or reduced any further using polynomials with integer coefficients. We'll talk about that a little more in a little bit, but for now, let's get to applying some factoring. Here we are on the Applications of Factoring worksheet. The first 6 problems here are just straight factoring to help you remember how to factor polynomials using different methods, such as difference of 2 squares, sum or difference of 2 cubes, factor by grouping, quadratic like trinomials, and more. So go ahead, pause the video here, and try and factor these 6 polynomials down to prime polynomial factors first. There will not be answers in this video, however, answers are available online. Please pause the video now and give these a try. We'll be moving on to question 7 in 3, 2, 1. Here we are at question 7. Question 7 looks like we are dividing 2 polynomials. In the numerator, b to the third minus 5b squared minus 50b, and in the denominator, b plus 5. As mentioned before, it might be useful to factor these to determine if there are any common factors in the numerator and the denominator that we can remove or cancel out. So let's check this out. The denominator, b plus 5, is already factored as far as it can go, but the numerator looks like it could use some work. First off, we have a greatest common factor of b. So let me take that b out. I'm left with b squared minus 5b minus 50. And again, in the denominator, I have b plus 5. No common factors yet, but I bet I can take this one step further. I realize that this is a trinomial, and I can factor by remembering what multiplies negative 50 and adds to negative 5. Well, that's going to be negative 10, so I can write b minus 10 as a factor, and positive 5, b plus 5. Don't forget the factor of b we already took out, and also the b plus 5 in the denominator. Now you might notice that there's a common factor of b plus 5 in the numerator and the denominator. B plus 5 divided by b plus 5 is 1, and so to signify that, I often like putting a giant number 1 over the b plus 5s to show that when I'm dividing them, they're equal to 1. In either way, they cancel out. I'm left with just b and b minus 10 as factors in the numerator. So after dividing, we're left with b times b minus 10. That's the answer in factored form. The answer in distributed or standard form would be b squared minus 10b. Now both are fine acceptable answers, although you might find one in the answer key and one not. It all depends on what the directions are asking for. Do they say leave your answer in factored form or in standard form? Then you'll choose which one to use. At this point, I'd like you to pause the video and try problems 8, 9, 10, 11, and 12. Unpause the video when you've got a handle on those, and we'll take a look at 13 together. Please pause the video. 13 will be coming up in 3, 2, 1, r to the 4th minus 27r over 4r squared minus 12r plus 9. Now it looks like there's going to be a lot of factoring going on here. So I'm going to factor the numerator and the denominator separately and then put them back together at the end once I'm done factoring. First, the numerator. We start with 8r to the 4th minus 27r. Right off the bat, I notice that there is a greatest common factor of r that I can divide out and be left with 8r to the 3rd minus 27. At this point, I realize that both of those terms are going to be cubic numbers, right? 8 is 2 cubed and 27 is 3 cubed. So I can write this as a difference of 2 cubes with an a of 2r and a b of 3. So using the pattern, remember to bring that down that r, we have 2r minus 3, and let's see, a squared, which would be 4r squared, plus a times b, which would be 6r, and then b squared, which would be 9. Perfect. So that is the numerator factored. What about the denominator? I'll do that in a different color. The denominator. Well, we start with 4r squared minus 12r plus 9. Now you could recognize that this you could use splitting the middle term and factor by grouping. Again, to split the middle term, you'd have to multiply the first term 4 and the last 9 together and get 36, and then figure out what numbers multiply to 36 and add negative 12, and then split the middle term and factor by grouping. But you could also recognize that this is a perfect square trinomial with a of 2r and b of 3. Remember, a perfect square trinomial is one where it has the pattern a squared. So if a is 2r, that's 4r squared. The last term is b squared, so it's, if b is 3, then 3 squared is 9. And the middle term is 2 times a times b, and 2 times 2r times 3 is, in fact, negative 12r. Oh, wait a second. Now I have to make this negative 3 right here. That'll do it. Okay, so negative 3 times 2r times 2 is negative 12r. Perfect. Okay, so that means that this factors into 2r minus 3 squared, or 2r minus 3 times 2r minus 3. Now that we've factored both the numerator and the denominator, I can rewrite this original expression like this. The numerator is now r times 2r minus 3 times 4r squared plus 6r plus 9. And in the denominator, we're left with 2r minus 3 and 2r minus 3. Now you'll notice a common factor of 2r minus 3 in both the numerator and the denominator. Okay, remember, dividing two numbers by themselves is equal to 1, so those will in effect cancel each other out, and we're left with r times 4r squared plus 6r plus 9 in the numerator, and in the denominator we just have 2r minus 3. Now, if they were asking for your answer in factored form, you'd be all set. If they want it in standard form, well, we just distribute this r through that trinomial and obtain 4r cubed plus 6r squared plus 9r, and the denominator stays the same at 2r minus 3. Go ahead and try number 14 at this point. When you're done, unpause the video, and we'll take a look at 15, 16, 17, and 18. Pause the video now. 15 is coming up in 3, 2, 1. Here we are at 15. Now in these problems, we're asked to find all the zeros, and it looks like the function is already factored for us. Now remember, zeros are when this function is equal to 0. So I'm going to put a little 0 right here. So 0 equals the factor x minus 3 and the factor x squared minus 3. Now, because of the zero product property, we can set each of these equal to 0. 0 equals x minus 3, and 0 equals x squared minus 3. So for the first one, that means that by adding 3 to both sides, we have that x equals 3. That's our first factor. For our second factor, wait a second, x squared minus 3. Shouldn't that be factored further? The answer is no. It's actually factored as far as it can be. This looks like it could be a difference of 2 squares, but in fact, it's not. 3 is not a square number. So we'll have to set it equal to 0 at this point and see what we can do. Luckily, this isn't that hard to solve. If we just add 3 to both sides, we obtain 3 equals x squared. And by taking a square root on both sides, and don't forget your plus or minus, we get that x equals plus or minus the square root of 3. So in fact, there are 3 solutions, or 3 zeros, to this problem. We've got x equals 3, and then x equals plus the square root of 3, and x equals minus the square root of 3. Not too bad. Let's also take a look at 17 together. So in 17, we have this first factor, x plus 4. And if we were trying to find the zeros, that's pretty easy. 0 equals x plus 4. And so x is going to be negative 4. Not too bad. But the second factor is a little more complicated. It's not a linear factor. In fact, it's a quadratic. And furthermore, it's a quadratic that won't factor any further. You can try to figure out numbers that multiply to 16 and add to negative 4, but you won't find any. Instead, we have to stop at this point, set it equal to 0 using the zero product property, and just solve it any way we can. Now, I already mentioned that we can't factor, and I don't really have time for completing the square, so let's just drop from the quadratic formula and see what we can do. Again, it does equal 0, so we are allowed to do that. My a term is 1, my b term is negative 4, and my c term is. So in the quadratic formula, we get 4 plus or minus the square root of 4 squared minus 4 times 1 times 16, all over 2 times 1. If I do a little bit of simplifying, especially under that square root, I end up with a negative 48 underneath that square root, and on the bottom just 2, because 2 times 1 is 2. Okay. From there, I know that the square root of negative 48, first off, it's going to have an imaginary number, and also simplifies to 4 square root 3, so 4 square root 3i. And lastly, I know that I have a 4 in all the terms in the numerator and a 2 in the denominator, so I can divide all of my terms by 2 and end with 2 plus or minus 2 square root 3i. So I've got 3 roots here. I've got one real root, the x equals negative 4, but I've also got 2 imaginary roots. I've got 2 plus 2 square root 3i and 2 minus 2 square root 3i. Now, the only reason this was really difficult wasn't the whole factoring, or wasn't really the setting equal to 0, the zero product property. It was that these, what we call prime factors, or quadratic irreducibles, remember from the beginning of this video, that couldn't be factored any farther. If you get something like that, it's a quadratic that cannot be factored, that's okay. Just set it equal to 0 like I have here, or here. At this point, I'd like you to try and finish out 16 and 18, and then try 19 to the end. Now, these last problems are just like the ones we've just done, except you need to factor them first. Hopefully, after factoring them, you only have linear factors, none of those quadratic irreducibles, and it's nice and easy to do the zero product property. But in the event that you do end up with a quadratic irreducible, something you can't factor, that's fine. Just set it equal to 0 and either, like I said, use taking square roots or the quadratic formula to finish solving. Good luck. Make sure to check your answers online.